Similarly, we can write the change of scale property, change of scale property. So if Fs is the Laplace transform of Ft defined for s greater than, let's say, alpha, and lambda is a positive constant, then the function defined by f of lambda s for s greater than alpha over lambda, then the inverse Laplace transform of Gs is equal to, so we know that the Laplace transform of f of t over lambda, this is nothing but, so this is for lambda greater than 0, and this is nothing but 1 over 1 by lambda multiplied by f of s over 1 over lambda. So this is lambda times f of lambda s, and this is defined, if f of s is defined for s greater than alpha, then this is defined for s greater than alpha by lambda. So therefore the inverse Laplace transform of this function Gs, which is f of lambda s defined for s greater than alpha over lambda, is simply 1 over lambda times f of t over lambda defined for t greater than 0. Now we have to be careful for not using this change of scale property for any real number lambda, because it only holds for positive lambda. For example, so this is a caution that it might fail for negative lambda. If we take the function ft given by the cosine integral t to infinity cos u over u du, then we have seen that the Laplace transform of this function is given by 1 over 2s ln s square plus 1 defined for s greater than 0. Now if we take lambda to be minus 1, so let me denote this Laplace transform as fs, then f of minus s is equal to minus f of s, because we have s here and s square here, so this change from s to minus s doesn't affect the log term, and s changes to minus s on the outside. So f of minus s is minus fs. On the other hand, 1 over minus 1 f of minus 1 times t, so this is the formula for our inverse Laplace transform for f of lambda s. Then this is given by minus t to infinity cos u over u du. So this is minus cosine integral of minus t, where t is greater than 0, but this is not defined. So the function, the cosine integral function is only defined, so CIT is only defined as a real function, as a real valued function on t positive. So even at t equal to 0, the limit does not exist. CIT does not exist. So the graph of CIX or CIT, it looks something like this. So it has a vertical asymptote near t equal to 0. So this is our CIT. So it goes to plus infinity at when you approach t from the right hand side. So we see that limit as t tends to 0 plus CIT goes to plus infinity. So it's not a finite value, and therefore it's not a piecewise continuous function near at 0. And we have to be careful using our formulas when these kind of functions appear, because you cannot use, for example, the derivative theorem. So this implies that the derivative theorem cannot be applied to this function. So in this case, in fact, in many places I have seen that once we define this function t to infinity cos u over u du, then people derive the function to get minus cos t over t, and then they take the Laplace transform of t f prime f t as minus Laplace transform of cos t, which is s over s square plus 1. But on the other hand, they use the derivative formula. So the Laplace transform of t f prime t, they use it as minus d over ds of s fs minus f0, and they treat this function, this limit f0 plus as a constant, and they simply write this as d over ds of sfs. So then you can solve a differential equation in fs to find the function fs, given that your right hand side is s over s square plus 1. But as you can see, this limit does not exist, and so this formula is not valid, is not a valid formula. Therefore this method, although it gives you the right answer, is incorrect, and you will see this done in many places. So we have to be careful when we apply the formulas that we have seen for Laplace transforms and the inverse Laplace transforms. We have to always check under what conditions these formulas are true. Otherwise you may get the right answer, you may not get the right answer, and sometimes you will get absurd answers. So one has to be careful. So now let me come to a new topic, which is the asymptotic behavior of the Laplace transform and inverse Laplace transform So by asymptotic behavior, we want to understand that if fs is the Laplace transform of ft, then we want to consider the limits as t goes to 0 plus ft. So this is f0 plus. Then we want to consider f infinity, which is the limit as t goes to infinity ft, and relate them to limits involving fs. So this is called the initial value of our input function, initial value. So this is for t near 0, t going to 0 from the right, and for t going to infinity, this is called the final value or terminal value. So these kinds of limiting behaviors or asymptotic behaviors are important when you try to model some physical problem in terms of differential equations, etc., and you want to know what kind of behavior this physical system will have when you evolve it for small time and when this physical system evolves for a very, very large time. So the small time problem is the initial value problem, and the large time problem is the final value problem. So in this respect, we have two theorems. So the first theorem is called the initial value theorem. This is called the initial value theorem, and this says that if ft is a piecewise continuous function on this interval 0 to infinity, and f prime t exists as a piecewise continuous function also on this function on this interval 0 to infinity, and f and f prime are of exponential order. Now suppose further that the limit as t goes to 0 plus ft equals L. So this limit exists. Then this theorem says that the limit as s tends to infinity, SFS is equal to this limit L. So provided this limit exists and these two are equal. So let's see the proof. So all our assumptions are made to be applicable for the derivative theorem. So by derivative theorem we have that the Laplace transform of f prime t is equal to s the Laplace transform of ft minus the limit as t tends to 0 plus f of t. This is nothing but L, and let us denote this as gs, and let us denote this as fs. So we have gs is sfs minus L. Now if we take the limit as s goes to infinity on both sides, then we see this implies that the limit as s goes to infinity, gs is equal to the limit as s tends to infinity, sfs minus L. So we have that the limit as s tends to infinity, gs is always 0 as f prime is piecewise continuous and of exponential order. So this is the asymptotic behavior of the Laplace transform as s goes to infinity, and we have seen this property before. So this implies that the limit as s goes to infinity, sfs minus L is equal to 0, and so this means that the limit as s goes to infinity, sfs is equal to L, and this is the same as t goes to 0 plus ft. So this is an easy proof when we have the assumptions that f is piecewise continuous, f prime is piecewise continuous, and both have exponential order. Then we can use the derivative theorem to prove it. But the theorem still holds if we only assume that that ft is piecewise continuous and of exponential order. So I am not assuming here that f prime is piecewise continuous. So this is piecewise continuous on 0 infinity. So the whole interval, and here I am not assuming anymore that the derivative f prime t exists as a piecewise continuous function and has exponential order, but this theorem still holds in this case as well. Now let's look at an application of the initial value theorem for evaluation of integrals. So suppose that ft is a piecewise continuous function on the interval 0 to infinity, such that the improper Riemann integral 0 to infinity fu du exists. So this is as an improper Riemann integral. Now if we define our function gt to be t to infinity fu du, and let gs, capital Gs, be the Laplace transform of gt, then this integral 0 to infinity fu du, which is nothing but the limit as t tends to 0 plus gt, this is going to be the limit as s goes to infinity s gs by the initial value theorem, So for example, let's take ft to be sine t over t, and so we have gt, the integral t to infinity sine u over u du. Now we have already computed the Laplace transform. The Laplace transform of gt gs is given by 1 over s tan inverse of s. This is valid for s positive, and so if we take the limit as s tends to infinity sgs, this is nothing but the limit s goes to infinity tan inverse of s, and we know that this is pi by 2, and so we see another proof that this integral, the sine integral, when evaluated from 0 to infinity, has value pi by 2. Similarly, we have a so-called final value theorem. So the final value theorem says that if ft is a piecewise continuous function on 0 to infinity, and the limit as t goes to infinity, so this is why this is the final value theorem, we take the limit at infinity, so this is f infinity exists and is equal to some value L, then the limit as s tends to 0, s 0 plus fsfs sfs exists and is also equal to L. So I will not give a proof of this theorem, it's a little bit more involved than the initial value theorem, but both these theorems are quite effective in solving various problems, and they will be especially important when we see how to solve ordinary differential equations using the Laplace transform technique. So let me just give a verification of this theorem, verification of final value theorem for a specific theorem for a specific example. So let me take ft to be sine t over t, and we know that the Laplace transform of this function is nothing but tan inverse of s for s greater than 0. So now note here that the final value theorem, in the final value theorem we must have fs. So this is an implicitly we can say that fs is defined for all s greater than 0, otherwise this limit as s tends to 0 plus doesn't make sense. So it's a necessary condition that the function should have a Laplace transform which is defined over all s greater than 0. So here we have this. Now let's try to compute the limit as t tends to infinity sine t over t, and one can easily check that this is 0 because sine t is bounded and you only have 1 over t function which is going to 0 at t equal to infinity. And here when the limit is taken for s tends to 0, sfs, this is the limit as s tends to 0 plus s tan inverse of s, but both limits exist at 0, so this is just 0 times 0, so this is also 0. So we can see that the final value theorem holds. Now both the initial and final value theorem can fail to hold. For example, failure of let's say initial value theorem. So for example, if you take ft to be t to infinity cos u over u du, so the cosine integral. Now note that the limit as t goes to 0 plus ft, the initial value does not exist. We have seen this, and now you can check that the limit as s tends to infinity sfs, this is given by the limit s tends to infinity s 1 over 2s times ln s square plus 1. So in this case, this limit s tends to infinity ln s square plus 1 also does not exist. So we cannot write an equation something like infinity equal to infinity, that doesn't make sense. So in this case the initial value theorem fails. It can also happen that one of them, if the limit t tends to 0 plus ft does not exist, then it could also happen that this limit on for the sfs as s goes to infinity is in fact finite. So let's see an example for this. So let's take, so this is first example. Let's take the function ft to be log of t. Then we have seen that the Laplace transform is given by gamma minus ln s over s, where gamma was the Euler-Mascheroni constant. And so if you take the initial value for ln t, this does not exist and goes to, this goes to minus infinity, and if you take the limit as s tends to infinity sfs, this is gamma minus limit as s goes to infinity ln s, so this also goes to minus infinity. So we see that again we have a absurd equation like minus infinity equal to infinity, which is meaningless. So the initial value theorem also fails because this limit as t goes to 0 does not exist. Let's see failure of final value theorem. So in this case we take ft to be e to the power t minus 1. So our fs is 1 over s minus 1 minus 1 over s, which is nothing but 1 over s times s minus 1. So of course the limit as t tends to infinity ft does not exist because we have a positive power of e does not exist, while the limit as s goes to 0 plus sfs is minus 1. So in this case this limit goes to infinity plus infinity, and this is minus 1, which is absurd. So in this case the final value theorem fails to hold. Similarly, you can take, for example, ft equals 1 minus sine t for t greater than or equal to 0. So we can easily compute the Laplace transform as 1 over s minus 1 over s square plus 1. So if you compute the limit as t goes to infinity ft, of course this does not exist, and it's not even something that goes to plus infinity or minus infinity. It's an oscillatory function, so it oscillates between 0 and 2 in fact, so it does not exist, while the limit as s goes to 0 sfs, this is 1 minus s times s square plus 1. So you take the limit s goes to 0 plus of this, but here you get 1. So you can see here that the final value theorem also does not hold, where the limit as t goes to infinity does not exist, it's oscillating, but on the other hand limit s tends to 0 sfs is finite.